Hello friend, welcome back again in this new ANSYS workbench session. In this session, we learn about how to solve 2D problems, plane stress, plane strain problems in ANSYS workbench. So to learn this, we'll start with a steel self bracket design. So the geometry of the bracket is given here. You can see that it is a kind of a L shape where length is from this end to the circle center 20 centimeter and the height is from top line to the circle center 12 centimeter. So we'll learn how to create this geometry in SpaceClaim, and once geometry is created, we'll take it in ANSYS modeling and use plane stress with thickness problem and assign a thickness of 0.2 centimeter. So then we'll apply the loads and get the stress on the part. So without any further delay, let's start with ANSYS workbench. So my ANSYS workbench is open, and now I'll pull the static structure in project schematic. So engineering data is by default stainless steel. We'll use it as is, will not make any change. Let's right click and go to the new space claim geometry. So space claim window is open now. Let's make some changes to the units. As we are going to work with centimeter, we'll change the grid size to show in centimeters. So length is defined by centimeters, and then instead of 0.1 centimeter grid size, we'll make it 1 centimeter. Okay, so let's right click and select new sketch plane and select the XY plane. Click on plane view to orient the plane to draw it. So let's start with two rectangular to make an L shape. So as discussed previously, the length is 20 centimeter up to circle center and the height is 12 centimeter. You can use your middle button to scroll in, scroll out, or zoom in, zoom out. So this is 20 centimeter and the width is 4 centimeter. Let's start from here. So 4 centimeter is already done. We need to make another 8 centimeter rectangular. Okay. Uh, you can click on this and first press escapes so that it starts, it does not draw rectangle. Okay, so if you want to adjust the width, you can take and select this line, pull in, pull out. So I want a width of 4 centimeter, so I'll do that. Now at the ends, we'll create circles with diameter is 4 centimeter. So I'll just press on 4 and click enter. Similarly, I'll create another circle with 4 centimeter here. Okay. Now to delete these unnecessary lines, we'll use this option called trim away. We'll select this. We have to click it twice because there are two lines from both of the rectangles. Click on these unwanted lines and curves and we'll get the L shape like this. Now we want to create a fillet here, say of the size 5 centimeter. So we'll select this create rounded corner option and click on this line and this line. It has created 4 centimeter. If you want to change, type 5 and enter, and it will create a 5 centimeter. Currently it is showing the dia. If you want to make but I wanted 10 centimeter radius, so I'll make, sorry, 5 centimeter radius, so I'll select 10. Okay, so this is the bracket I wanted, and it has been created now. Now let's insert some circles of diameter 2 centimeter. Okay, I want to insert another circle at this location, so the center will be aligned from with these two circle centers. Again, diameter 2 centimeter. So our geometry is created here. Now if you see, this is a line geometry. If you want to create a circle, we can simply go to 3D mode and it will create a circle, or you can select on pull and automatically it will create the surface. Okay, so because we don't want these small circles, we'll select them and delete them. So let's click on it and press delete and press delete. So with this, our SpaceClaim geometry is created. Now we'll close the SpaceClaim and go to the ANSYS modeling. Okay, so just right click on the model and open it. I already opened here. So SpaceClaim geometry is already imported here, and we can change some properties. So you can see currently it is showing the question mark on the surface. So let's select on the surface and check what's wrong with this. Okay, so it is saying that thickness is 0 meter, uh, and dimension shown is 3D. So instead of 3D, we'll make it 2D to use 2D plane stress with thickness option. And once you select on the 2D, it says 2D behavior is axisymmetric. We'll by default it is axisymmetric. We'll change it to plane stress. Uh, Based on the problem, you can choose other options, but currently our problem is plane stress with thickness, so we'll select plane stress and assign a thickness of 0.002 meter or 0.2 centimeter. Okay, so thickness is assigned, and now you can see there is a green tick mark, so that's good, our geometry is done. Now let's go to the mesh and use the default setting, update the mesh. It may take some time. Okay, so our mesh is created, and once it is done, we can start assigning the boundary conditions to the part. So I'll right click on the static structure and insert a fixed support and select this line and apply. So this edge is completely fixed now, and remember we have to apply a pressure of 250 Newton per centimeter square. So we need to convert this in meter and apply in on this top line. Okay, so let's right click and insert pressure. So I clicked on the pressure and select the line here and apply. So currently pressure is applied, defined by normal to surface, and it is shown 0 Pascal. So 250 Newton per centimeter is equal to 2.5 megapascal. So we'll give 2.5 e to the power 6, and pressure is applied. So let's see what kind of deformation it causes on the part, the 250 or 2.5 megapascal pressure. So we'll insert directional deformation on the solution side, and let's insert the stress equivalent or von Mises stress, so that we can see stress on our part and optimize the geometry or check whether it is meeting the yield stress requirement or not. So we apply the fixed support on this line, pressure on the top line, and on the solution section we are interested in deformation of the part and equivalent stress. So all the inputs are done. Now we can go ahead and solve this. So just right click and solve. Wait for some moment. So our solution is completed, and now we can plot the deformation. So being this end supported, this is the this is how parts should deform. So looks like our model is working fine. Let's see what is the equivalent stress on the part. So I'll just click on the equivalent stress, and max stress is coming out to be 7.5 e to the power 7 or 75 megapascal, and the highest stress is on this fillet. So currently we are using large mesh for educational purpose, but I don't think these many elements are properly capturing this fillet. It is better to have a fine mesh in this region because this is our max stress region. So I'll not go and change these things, but if you're trying this model, you can try to refine this mesh size on this fillet and check how much it will increase. But currently it seems like the stress is around 75 megapascal, and based on this problem the yield stress for steel is 250 megapascal, and we want to have a factor of safety of 2.5, which means that our stress should not go beyond 100 megapascal. So I think we meet that criteria. In fact, we have 25 megapascal margin. So we can play around this geometry so that we can make it more cost or weight effective, whatever is your target. So probably you can increase this circle size, and you can see that stress in this particular region is very less. So maybe you can insert a rectangular, instead of circular hole, a rectangular hole here to take out some additional material. Probably you can increase the circle size here or reduce the plate size here to optimize the geometry. Uh, that's all in this session. Please let me know if you have any question in comment box. Thank you for watching. Let me know your feedback.